Let omega be the circle of radius 4 centered at minus 23, 27, and let A be the origin and B equal 5, 5. If P is the point on omega for which angle APB is maximized, and PA over PB squared can be expressed in the form little a over little b, where A and B are relatively prime positive integers, find B. We have the circle omega of radius 4 centered at minus 23, 27, and we also have points A at the origin and B equals 5, 5. Now we want to know what point P on omega will get angle APB maximized, which is this angle over here. And to maximize that angle, we're going to have to use the extended law of sines, because we know that A and B are fixed points, and APB is an angle that varies as P moves along omega. And because A and B are fixed points, the distance between them is always the same. So it makes sense to use the extended law of sines. So using that, we have AB, which is fixed, over the sine of angle APB, which is obviously an acute angle given how far P is from A and B, which are relatively close together. And P is near minus 23, 27. So AB over sine of angle APB, which is an acute angle, is equal to 2 times the radius of the circumcircle of APB. Let's add that in. There we go. That's the circumcircle of APB. And this expression, AB over the sine of angle APB, is 2 times the radius of this circle. So if we want to maximize angle APB, which since it's an acute angle, will also maximize sine of angle APB. So this expression here is maximized. That means AB, which is fixed, it's 5 root 2, the distance between A and B. AB over sine of angle APB, the denominator is maximized, so 2r, this is going to be minimized. We want the minimum r, the minimum radius of the circumcircle of triangle APB. So we just choose the tangent point P, because that way we won't have any smaller circles that pass through A, B, and a point on omega. Because if it wasn't the tangency point, it would intersect at 2 points, and any point, you can choose any point on the minor arc, and that would have a smaller radius. For example, if we enlarge APB, the circle, to this, then you can just choose any point on this minor arc and make the circle smaller. So it makes sense that P is the tangency point. So by now we've established that P is the tangency point between a circle that passes through A and B, and circle omega, which has center minus 23, 27, and radius 4. So in that case, when the two circles are tangent, we want to find PA over PB squared. The first observation we want to make here is that P lies on the center line. The center line is the line that connects the centers of the two circles. I'll call them C and D. But let's just connect the centers of the two circles. This is C, and that's D. And we know that AC is equal to R, as is equal to CP. And DP is equal to 4. That's the radius of circle omega. And we know AD is just the square root of 23 squared plus 27 squared. So AD is the square root of 23 squared is 529, 27 squared is 729. So that's equal to the square root of 1258. So let me write that here. The square root of 1258. And I'll call PA equal to D1. And PB will be D2 later. So you know what theorem we're going to use now. It's Stewart's theorem of man plus dad equals bomb plus sink. Let's use that here. So we have 4 times R times 4 plus R. And then plus D1 squared times 4 plus R is equal to the square root of 1258 times R times the square root of 1258, which is just 1258R. And then plus R times 4 times R, which is just 4R squared. So both the left-hand terms have 4 plus R in them, which means we might want to break the right side down into some term that has a factor of 4 plus R in it and another one that doesn't. So we know that 16R plus 4R squared is just 4 plus R times 4R. Rewriting this, we have 4 plus R times 4R plus D1 squared times 4 plus R. And then we want to break the 1258R, split it up into 16R and 1242R, so that the 16R can go with the 4R squared to create 4R times 4 plus R. And then we're left with 1242R. Now we can cancel the 4r times 4 plus r, and we're just left with d1 squared equals 1242 times r over 4 plus r. Similarly, we can use Stewart's theorem on triangle BCD as we did on ACD just now. We have BC is equal to r as well, and we have BP is equal to, I'll call that D2, and then BD is equal to the square root of 23 plus 5 squared, which is 28 squared, plus 27 minus 5 squared, which is 22 squared. And that's equal to the square root of 784 plus 484. And that's equal to the square root of 1268. So BD is equal to the square root of 1268. And now we can use Stewart's theorem. So again, we have 4r times 4 plus r plus d2 squared times 4 plus r, in this case, is equal to the square root of 1268 times r times the square root of 1268. That's just 1268r. And then r times 4 times r is going to be equal to 4r squared. So now, as we did before, we can split the right side up into 4r squared plus 16r and 1252r. So then we would have 4r times 4 plus r plus d2 squared times 4 plus r equals 4r times 4 plus r, which is 4r squared plus 16r, and then what's remaining is 1252r. So we can cancel the 4r times 4 plus r. We're left with d2 squared equals 1252 times r over 4 plus r. We want PA over PB squared, which is d1 squared over d2 squared. And we have d1 over d2 squared equals 1242 over 1252, since the r over 4 plus r's cancel out. So this is equal to 1242 over 1252, and that's equal to 621 over 626, if little a and little b are relatively prime. So b is equal to 626. Thank you for watching my YouTube video, and please follow my channel.